A 0.3 cubic meter tank contains saturated refrigerant 134A at 14 degrees Celsius. At this initial state, 55% of the mass of the refrigerant is in the vapor phase. A valve on the tank is connected to a supply line containing refrigerant 134A at 1.4 megapascal and 100 degrees Celsius. The valve is now opened and refrigerant enters the tank. When the pressure in the tank reaches 1 megapascal, it is observed that only vapor remains in the tank, at which point the valve is closed. Determine the final temperature, the mass of the refrigerant that enters the tank, and the total heat transfer for this process. So let's begin this problem with an appropriate illustration. So we're told that we have a tank and that this tank contains refrigerant 134A and that the volume of this tank is 0.3 cubic meters. We're also told that this tank contains saturated refrigerant and that 55% of this initial mass of the refrigerant is in the vapor phase. So in other words, we know the initial quality of 0.55. So let's just let 1 equal the initial state. We'll let 2 equal the final state. And as such, we know that T1 is 14 degrees Celsius and the quality at 1 is 0.55. Now, further we're told that there's a valve on top of this tank that is connected to a supply line, and this supply line is the inlet to this particular tank. So I is the inlet, and we're told that the pressure at the inlet is 1.4 megapascal. So PI is 1.4 megapascal. And we're also told that the temperature of this inlet stream is 100 degrees Celsius. Now we're told that the valve is opened and the refrigerant enters the tank, and when the pressure finally reaches 1 megapascal, it's observed that only vapor remains in the tank. So this tells us then that the final pressure is known, so P2 is 1 megapascal, and also since only vapor remains, the last drop of the liquid in this two-phase mixture is finally vaporized, so that's the point that we call the saturated vapor. So basically 2 is a saturated vapor. So you can see that we know two independent properties at both the initial and final state as well as at the inlet state. So all of our thermodynamic properties that we need for this process are going to be known to us. Finally, we're asked to find some things. We need to find the final temperature, so T2 is an unknown. We're also asked to find the mass that has entered the tank, so MI, the mass of inlet, is unknown. And lastly, we're trying to find the total amount of heat transfer, so Q is also going to be unknown. Now, in order for us to find the temperature at the final state, we really have to do nothing. We know the final state. It's a saturated vapor. So let's just find that right away. So at P2, T2 is just equal to the saturation temperature. We're going to go into table A12 for the refrigerant, and that saturation temperature then is known to us. It's 39.4 degrees Celsius. So that part's pretty easy. Next, how might we find the mass at the inlet? Well, here, let's just remember that from our conservation of mass or continuity equation, the mass that flows in has to equal the difference between the mass that we end with and the mass that we begin with. So MI is going to equal M2 minus M1. So the question now is, how do we find M2 and M1? Well, again, we know the thermodynamic state, we know the volume, so we can find either of those masses by just dividing the volume by the specific volume. So M1 is going to be V over specific volume V1. M2 is going to be the total volume V divided by the specific volume V2. Once we look up the thermodynamic property data at 1 and 2, we just plug them into this equation. We know the volume, and we can get the mass at the inlet. Now, what about finding the heat transfer for this particular problem? Well, this is a charging problem, and to find the heat transfer, we simply have to use the first law of thermodynamics. So the first law for charging problems is basically the following. The amount of heat transfer into the system, Q, is simply going to equal the mass at 2 times the internal energy at 2 minus the mass 1 times the internal energy at 1, and then minus the mass at the inlet times the enthalpy at the inlet. This is our equation for a charging problem. Keep in mind that this is only a single inlet, right? There's no exit streams, just an inlet stream, so this is the appropriate equation. Let's also note that like essentially all of these charging and discharging problems, there's not going to be any mechanical work. There's no mixing devices or shaft work or anything like that. Also, there's no kinetic or potential energy changes associated with any of the substances in this process. So that all gets neglected. That's typical of all these types of problems. So now, in order to find the heat transfer, we simply have to solve this particular equation. And again, that's not difficult. We know the thermodynamic states at 1 and 2 and at the inlet. We already have seen from directly above how to find the mass, initial and final, as well as the mass at the inlet. So it's really just a matter now of finding all of our appropriate thermodynamic properties, getting those masses, internal energies, and enthalpies, and finishing up the problem. So let's go ahead and do that. Let's find our thermodynamic property data first. So at the initial conditions, at T1 and at the quality at 1, here, for this two-phase mixture, we'll have to go into table A11. Let's find the specific volume first. So the specific volume V1 is just VF plus the quality at 1 times VFG. As usual, our textbook has no VFG data, so we'll just find it by taking the difference between VG and VF. So let's just pull the data out of our table. 0.0008018 is HF. The quality is 0.55. HG is 0.04347. So VG minus 0.0008018. And this then allows us to find the initial specific volume of 0.02427. And our units here are all cubic meters per kilogram. Next, let's find the internal energy at 1. So U1 is UF plus the quality times UFG. UF is 70.56. UFG is 167.30. And we can go through the math and we get 162.57 kilojoules per kilogram. All right, so now we have our data at 1. Let's move on to state point 2. Point 2 is a saturated vapor. So at P2, we'll go into table A12, and the specific volume, V2, is just Vg at this particular pressure. So that's 0.02033 cubic meters per kilogram. And additionally, U2 is equal to Ug, so that's 250.71 kilojoules per kilogram. And then lastly, let's find our enthalpy at the inlet. So here at the pressure and the temperature at the inlet, at these particular conditions, we'll find that this is superheated vapor. So we're going to have to go into table A13. So we go into the 1.4 megapascal subtable, we read down to the 100 degrees Celsius line, and we get the enthalpy of that inlet flow stream as 330.32 kilojoules per kilogram. So now we have all the data we need. Let's find our masses. So M1 is the volume over the specific volume V1. So we get 0.3 cubic meters divided by 0.02427 cubic meters per kilogram. And this gives me the initial mass in the system of 12.36 kilograms. M2 is found similarly. So this is the total volume over the specific volume. So the units are the same. We get 0.3 divided by 0.02033. So the final mass is going to be 14.76 kilograms. And then the mass that flows in has to be the difference between the two masses above. So we just take that difference and we get 2.40 kilograms. So now let's just complete this problem by solving for the first law. So back to our first law equation. So the heat transfer is going to equal M2U2, so 14.76 kilograms multiplied by 250.71 kilojoules per kilogram, and then minus 12.36 kilograms multiplied by 162.57 kilojoules per kilogram, and then minus MIHI, so minus 2.40 kilograms times the enthalpy, which is 330.32 kilojoules per kilogram. And if we go through the mathematics, we get that the heat transfer is 899 kilojoules.